So I'm going to talk about real-time path integral methods, and let's see, I was planning to give a short introduction since I'm the first speaker, even though I realize that all of you here are experts. So if it's too boring, let me know and I'll completely skip the slides, right? So we are looking at quantum dynamics in condensed phase systems or large systems. And very often we're interested in the dynamics of a system that is embedded in a large environment. The system itself could be a small particle like a proton or electron transfer pair or a group of electronic states and so on. And the isolated system would show all the effects, all the quantum mechanical effects that we're familiar with, but the system is embedded in a large environment. The environment tends to suppress some of the quantum effects, introduce decoherence, and eventually take the system to equilibrium. So since we're interested in the system, when I say system, I refer to what we are probing directly. We are going to be computing the reduced density matrix, which is the density matrix propagated time t traced with respect to all the degrees of freedom of the environment. How do we calculate this? In principle, we could do this by solving the time-dependent Schrödinger equation, one wave function at a time. However, we all know that this is extremely expensive and it is prohibitive when we have thousands of degrees of freedom. And at the same time, even if we could compute a wave function, we would have to do a very large number of calculations to propagate all the thermally populated states one by one. So instead, we're going to be working with a path integral formulation. And again, I assume everyone here is familiar with it. Very quickly, it is a generalization of the double slit experiment. And it is an expression, a formulation based on the idea of quantum superposition. So the quantum mechanical amplitude to get from here to there is equal to the sum of amplitudes along all possible paths that the system could follow. This is a full quantum mechanical result. From this one could derive the time-dependent Schrödinger equation. So it contains, all the quantum mechanical effects, such as interference, tunneling, delocalization, tail balance, decoherence, and everything comes from the interference, constructive or destructive, among those phases. Note that the quantum mechanical amplitude along a path, any particular path, has a modulus equal to 1. So they're all important in terms of their weight. And that's a nightmare computationally. And the computational practical advantage and the practical appeal of this is that no wave functions are needed. So if one could compute the sum, then one could have exact quantum dynamics without having to store multidimensional wave functions. If one takes the idea and discretizes a path on a computer by discretizing the spatial coordinate and the time onto a grid and the time in space and time, then one sees that the number of paths grows exponentially with the total number of time steps, which means that even if we have a two-state system and propagate for 100 time steps, we're going to have 2 to the 100th power paths, and that's an astronomical number. These are numbers that you cannot sum, let alone when you go to multidimensional systems with lots of states and lots of degrees of freedom, you can't really do this at all. At the same time, since the quantum mechanical amplitude is highly oscillatory, Monte Carlo methods fail entirely. They run into a massive sign problem, and you cannot just sample those paths. And we all know here that if we were to turn the time into imaginary, we would get equilibrium quantum statistical mechanics, for which the I factor turns into a negative sign, and everything is nice and friendly. But in imaginary time, we don't have dynamics. We only have statistical mechanics, equilibrium properties, and we can extract dynamics only as an approximation with certain assumptions. So we're going to stick to real time. And to overcome these fundamental problems with the original formulation of a path integral that makes it so unstable and not so friendly computationally, we're going to have to follow a different strategy. The idea is to represent a system in terms of a minimal number of discrete states. We're going to write the path integral expression in this discrete basis, We're going to use physically motivated propagators and integrate out the environment analytically or numerically to get an influence functional. And then we're going to exploit the physics and see if we can devise certain decompositions that allow us to evaluate the path integral by quadratures, and this way to circumvent the sign problem. And I'm going to start with system bath dynamics. We have a system coupled to a large number of harmonic oscillators, a harmonic bath. This applies to a lot of processes in the condensed phase, where the bath could consist of molecular vibrations at the normal mode level, or phonons, or even fictitious modes if you're modeling a liquid. And it's relevant to a lot of problems. And the properties, the parameters of the bath are collectively captured in the spectral density function. So a long time ago, actually 30 years ago, we started developing this methodology that became known as the QAPI, for quasi-adiabatic propagator path integral. The first steps were to construct physically motivated propagators by splitting the time evolution operator along the adiabatic path. This is actually how this started. Many of you probably have not seen very much of this because you are looking now at discrete problems, but we started with continuous systems. And we had to discretize the spatial coordinate into the plan was to evaluate everything by quadrature. So we need a grid that's as compact as possible. So we constructed a grid based on discrete variable representations, which are obtained from the eigenstates of system Hamiltonian, transformed to DVR states. And all this gives us a very good starting point that minimizes the number of time steps by having good propagators, minimize the number of states that we need, or grid points that we need to include in the sum. Now, the unique advantage of the path integral in the case of a harmonic path is that the harmonic path harmonic degrees can be integrated out analytically because they're Gaussian functions, and they give us an influence functional that modifies the amplitude of the system. And if I'm going to use these diagrams, if I had only the system, an isolated system, then and here I'm representing I'm drawing the path integral variables as black dots, and these connections are the connections that are in the quantum mechanical propagators appear in the expression. So for an isolated system, we only have couplings between the variables that couple adjacent time points, and that's because the system is equivalent to a time-dependent Schrödinger equation, first order differential equation. So there's no memory, and we just get nearest neighbor couplings here, Markovian dynamics. In that case, we could evaluate the reduced density matrix just the same way we would propagate a wave function by eliminating the variables one at a time by doing matrix multiplication. However, when the system is coupled to a harmonic path or to any environment, we get an influence functional that introduces non-local interactions in time, and all the variables are now coupled like this. So we can no longer evaluate this one step at a time because all the variables are entangled together. And this entanglement is known as time non-locality or memory that appears from the influence functional. So fortunately, it turns out that the memory that comes from condensed phase environments has a finite span. And that's because those influence functional coefficients are given by time correlation functions of the environment, and these decay irreversibly if the environment is macroscopic, as Avogadro's number of degrees of freedom, which means that when we look at this diagram, not every variable is coupled to every other variable, but it's only coupled to variables that are within a certain distance in time, which is the memory time. And then you get this structure. And then one sees easily that I can decompose the full path sum into a series of iterative operations, where instead of, which is kind of similar to the matrix multiplications in the case of an isolated system, but now because of memory, we have to include all the variables that span, or all the time points that span the memory length in a tensor. So we go from having a matrix, propagating a matrix or a vector, if it were to be a wave function, to propagating a tensor by multiplying by another tensor. So here's the tensor of the path segments that span the memory length, and here's the propagator tensor that couples these blue variables to the yellow variables, and so on. Once you can do this one time, you can do it any number of times. So you propagate iteratively in times. And since this iterative in time, we turn the exponential scaling with the number of time steps into linear scaling. So we're working with tensors here. And this is the first tensor decomposition I'm aware of a path integral. In fact, we wrote a couple of papers and we put tensor in the title of those papers. And then at that time, this was early 90s, I was advised by colleagues that I should drop the word tensor from the title because the chemists were not reading it. All right, it was too scary, in other words. All right, who would have thought? All right, so again, we get linear scaling. We have, with this, QAPI is completely general as far as the properties of the bath. We have no restriction on the form of spectral density. If I do the full evaluation here, the way I described it, I'm going to have to store n, little n, to the two delta k max elements. This parameter delta k max is what we call the memory length, the number of times they're spanning the memory. And little n is the number of states of the system or grid points. So if I drop nothing, this is what I need to store. In practice, we even those first very early days, we did not store this in general. Where we did back then in the mid-90s, we did a simulation of electron transfer in photosynthesis with three states and with a memory length that was 35 units. And this would not have been possible. We had to store everything. So what we did is we applied filtering techniques, realizing that the vast majority of those paths that span the memory length have exponentially small weights. We don't need to include them at all. So if you can find what you have to include and what you don't, then you get a lot less on this. In some regimes, though, you do have to include all those terms. And there are a number of methods that have been developed for overcoming this. As I said, filtering, I will mention blip decomposition, and MPS or with SVD and so on can reduce the number of paths. So this is the original QAPI. All right, so how can we do better than this? The blip decomposition is one idea. So if I look at the reduced density matrix, there are two time evolution operators, the one forward in time and one backward in time. And this structure gives rise to pairs of paths, forward and backward paths, that look like this. In general, they are different, they're distinct. And this is important for quantum interference. All of quantum interference comes from phases that phase differences among those different forward and backward paths. If, however, you change the variables, okay, so before I do that, so if I take this drawing here and turn it into a diagram for discrete time, it looks like this. In other words, the forward and backward paths can either be the same over a time step or be different. And then we get this kind of structure here. Forward and backward are same, different. And the time steps where the forward and backward paths are different are called blips. Going back to Tony Leggett's non-interacting blip approximation, that's where the term comes from. So if you look at the path integral, the evenless functional structure, you realize that between blips, we have no interactions except those that are shown here as dashed lines coming from a blip that is forward, that is in the future, that the blips are in the future, which means we can evaluate the sum over all the path integral variables in between blips without doing the full path sum. We can do this iteratively by matrix multiplications. So if I have 10 time points between two blips, I would have, for a two-state system, I would have 4 to the 10th paths to sum over. However, instead of doing this, I can do 10 2x2 matrix multiplications, which is nothing. So this gives us, when you do the full calculation, you analyze what you have here, it turns the scaling, the number of operations from n to the 2 delta k max to this number, to the k max power. And what you see here is the n squared turns to n squared over 2. So for a two-state system, plus 1/2, for a two-state system, instead of doing 4 to the memory length power, you do 3 to the memory length power, and that's exponential speed up and of the calculation. So, and that's still exact here. So I'm evaluating the entire path sum. I'm not dropping anything. So you get this exponential acceleration without dropping anything. Now, in addition to this, if we think about the contributions of those 4 backward path pairs, if we go toward the incoherent regime where the temperature is high and the system bath coupling is large, then the bath tends to suppress quantum coherence. So what you get is the vast majority of paths that differ a lot for back pairs that differ significantly, they don't contribute. They contribute 0. In other words, multi-blip path pairs have exponentially small contributions. And when you recognize this, you realize that you can use the number of blips as a systematic filtering criterion. So you can start by including the 1 blip paths, 2 blip paths, and 3, and so on. And this converges very rapidly in the incoherent regime. So what you get is convergence to exact results with B, the number of blips, being much, much shorter than memory. So you can do calculations where you have, say, 200 steps of memory, you can do them with 3 or 4 blips, and it goes very fast. And so this reduces the storage as well as the number of calculations by exponential factors. All right, so a few years ago, Jonathan Keeling and Peter Kierdan and collaborators worked out a very nice decomposition, a different decomposition of the QAPI tensor in terms of matrix product states. And the expression takes this form. This is my own visual representation of this, diagrammatic representation of this. So at each time point, you have a matrix, and you multiply those matrices, and the dimensions of the matrices or bond dimensions would grow as the number of paths if you did nothing else. But now you can use SVD to compress those tensors, or I should say a better word, to filter out the redundancy in those tensors. That's the way I think about this. And once you eliminate that redundancy, you get much more compact matrices that can have low dimensions, really, depending on the parameters, and you can have matrices. You can have matrix dimensions here that are much lower, smaller than the number of paths. So this works very well, I think, for in the weak coupling regime, I would say, and for small systems. The most expensive part of this is to compute SVDs. SVD scales as a cube of the bond dimension. So if these matrices get large, then I think that becomes problematic. What else can we do here to improve this? So here's our latest. Which is to a way to disentangle the path-renal variables one at a time. So here is the fully entangled structure of the path integral. And even though all the variables are fully entangled within the memory length, it turns out that, and I did not know this a few years ago, I've been thinking about this for many years, it turns out that you can disentangle a structure one variable at a time by recursively shifting the entanglement of the path-renal variables to longer and longer times, until eventually it disappears, just like memory disappears. So when you do this, what you get is the reduced density matrix becomes a sum of matrix products, matrix multiplications. And this is not an MPS at all. It is a sum of matrices. And unlike the previous slide, these matrices are of fixed dimension equal to the dimension of the reduced density matrix. So we're summing these products here. And M is the M's here are little n square by n square matrices. And where the row that I'm using here is the reduced density matrix of the system from all possible initial conditions. That's why these are n square by n square. So this is an exact analytically derived decomposition. Yes.
Sorry, just a question. Is this the same as transfer tensor?
No.
No.
No. Okay. It is not. It's an analytically derived decomposition of the influence functional term by term. It looks similar, has a similar structure, but it's not the same. So again, only small matrices are involved. Our max here is the entanglement length. at the beginning, or very often I would say in practice, Rmax is equal to the memory length. However, Rmax is a separate convergence parameter in principle. And very interestingly, Rmax can be much lower than the memory length. So you can have situations where the memory is very long and Rmax is short, really depends. So once you have this structure, then what you need is to compute those matrices. You compute those matrices by doing calculations within the memory length. And this can be done by any method of choice, the non-iterative part. And just very quickly to show how this works, here is, oh, I apologize, this came from another talk, all right? The notation, this is supposed to be the rho tilde, the same thing, the U. All right, so here is what it is. It is the full path sum has this form, K are the short time propagators and F is the influence functional. And let's say, for example, that I have a memory length equal to 2 units. Then the reduced density matrix is given by this expression. I have 2, 2, 2, 1, and 2, 0 interactions, as well as 1, 0 interactions. And sorry, I should be looking here actually. Right, so see better. All right, so this can be done to go to the time point 2. I simply, at this point, still, I can do a matrix multiplication of factors that are propagators, 0, 1, 1, 2, and the 0, 2 influence functional can be included at the end. That's straightforward. But the moment I go to the third time step, I have a double sum. And that means that this is no longer a matrix product, and I need to, then it looks like I cannot disentangle this sum, right? I cannot turn it into a single sum. However, notice that an identity, that if I take this product, this is the influence functional between time variables 3 and 1, and that's between 2 and 0. If I multiply those out, I can express this in this form. Don't ask how I came up with this, but that's an exact identity. You can check by multiplying this that you get this. So noticing this identity, I can take this expression here, the RDM at time 3, and decompose it like this. A matrix that connects time points 3 and 2, and the one that connects time point and the reduced density matrix at time 2, and then a 3, 1 matrix times 1, 0. And that's not the end. I have something left over, which I call the remainder, or whatever, residual of this multiplication, of this decomposition. And now this is given by, here, is given by that stuff that came from those terms here, right? So it has this form. And notice that what I have here is, instead of having F31, the influence functional between beats 3 and 1, I have now F31 minus 1 and 2, 0 minus 1. And this is important because the influence functional here, this is a full exponential function, right, of those influence functional coefficients and so on. So that's an exponential of a quantity, and the whole exponential tends to be of order 1, because if my time step is reasonable and not huge, those influence functional coefficients will be small, will be close to 0. So because these factors are close to 1, then when I subtract 1, the way these appear in this expression, I get something small. So this is going to be small, right? So let's continue like this. And this is the grammatic representation of this decomposition here. Continue like this. And if I go to the fourth time step and I write down the path integral, and I now have a triple sum to begin with. So I use a similar decomposition of the influence functional product, and I can turn it in this form. And now I have a residual that is a matrix M40. And that's again these are fully entangled remainders that we get. Entanglement doesn't disappear. It's just shifted to these terms here that I call remainders. And the structure of this is given by this. And notice again that I have this structure of F minus 1 in these factors, which means that this is going to be small. And notice that there is an extra factor compared to M30. Now there were 2 of these factors, F minus 1 factors, and now there are 3. So this is actually smaller than the previous one. And it keeps going like this. So if you keep doing this, you end up with the compositions like this and a remainder, and the remainder keeps getting smaller and smaller as you keep going, which means eventually it disappears. And here is a numerical calculation of how it disappears. You can see this remainder here. This is a log scale, so it drops exponentially actually. So with memory length of equal to 2, memory length equal to 3, it drops like this and eventually disappears. Yes?
Supposed to. Okay. Do I understand the size of the Hilbert space is kind of fixed once and for all during all of this? Like you've restricted the state space to a reasonably small set.
I'm starting with a system. I've discretized a system if it continues to coordinate to a small number of states, which are
small, like 3, 10, does it matter?
20,
20, okay.
25, 30, okay, something like that.
So and that's that little n in the
That's
cell?
a little n.
Right.
Mhm.
I see. So right, so you have small bracket. This looks like characterization in the sense that you have small things, but then if you actually did the sum, there would be big, you know. Okay.
Where, what was it?
No, what I'm saying is that the size of the Hilbert space, by keeping it finite, you're able to control the expansion. But you know,
I do think this is related to the size of the Hilbert space. So we start with
the space which you kept for integration.
So you can have a system that starts out by being discrete, by having, say, a certain number of electronic states. So then it's a full Hilbert space.
All right, thank you.
Yeah. All right, so again, this summarizes what I was saying for all the different memory lengths. So it goes like this. So basically this converges with respect to this length called the entanglement length, and very often this is equal to a memory length, but again, it really depends, could be smaller than that. So again, this is the form. This is a graphical decomposition of what I was showing you, those influence functional factors, and I thought I had replaced that figure with another one. All right, no, that was previous slide. All right, and we can, as I said, we can go to extended memory with a trick, and we can have memory that's much less than we can have entanglement that's much smaller than the memory parameter. All right, so, okay, so now if we have interacting, we go beyond the simple system bath, and we have a number of interacting system bath units, which could be molecular units that are interacting in a molecular aggregate. Then how can we approach this? Now, if I have, if the states on each monomer are, say, if each monomer has a spin or has 2 electronic states, and I've got 20 monomers coupled together, then the total number of states is 2 to the 20th, which is 1,000,000. So I could take this, and each of these units has its own harmonic path. I could take this and turn it in and call it a new system bath Hamiltonian. However, the number of states will be enormous, and you can't really do very much with these in these situations. So what we do is something different. We have developed a method that we call the modular path integral. We decompose the path integral into modules, and in this, getting ahead of myself here. Here it is. In this, in a simple form, if I have nearest neighbor interactions, it doesn't have to be like this. I get a diagram where I write down the path integral variables for each unit, and here it is, unit number 1, number 2, and so on, like this, and they connect like this. They might also connect in different ways, more complex ways, but these are details. And then we can evaluate the path integral by summing the variables over 1 unit at a time. So and this gives us linear scaling with aggregate length. And now let's move to anharmonic environments. I'm just telling you what we can do, basically all the things that we can do up to now. So if I have an anharmonic environment, it's like a solvent or a biological environment, and I don't want to turn this to a harmonic bath the usual ways by making assumptions, then I need to deal with something that is beyond the capabilities of a Feynman-Vernon influence functional. So it makes sense that we would need to resort to a classical trajectory method for something that's fully coupled and harmonic many-body environment. In that case, if we only had a liquid, then we could treat it very successfully by using quasi-classical methods like LSC-IVR or forward-back or semi-classical dynamics. And this can be, it can capture some quantum effects and can be very reasonably accurate, pretty accurate actually, and as well as very efficient. But the problem is that we need to treat the quantum mechanical system interacting with this environment. So in the system here needs to, by assumption, needs to be treated by full quantum mechanics. So how can we couple a quantum description of a system with a classical description of the environment? That's a well-known century-old problem known as the Ehrenfest dilemma. And the problem is that quantum and classical mechanics have very different structures. A classical trajectory needs to know the force at each phase space point. However, if the quantum mechanical particle is delocalized by expressed in terms of a wave function, then where do you evaluate that force? And according to the Ehrenfest prescription, you take the average of the force, and that leads to mean field type of theories, which are pretty bad. Actually, they don't capture the tail balance and they don't give you correct branching ratios and so on. So methods like surface hopping were developed to overcome this situation. However, within the path integral formulation, the problem entirely disappears because the quantum mechanical particle is described in a local way. The quantum paths of a system are local, one path at a time, and a quantum path can interact, can talk to a classical trajectory uniquely and unambiguously without any need for any additional assumptions. So this gives rise to a rigorous quantum classical formulation of dynamics that we call the quantum classical path integral, or QCPI. And this is derived, rigorously derived. We start with path integral in the space of all degrees of freedom, system and environment. And then we apply the stationary phase approximation to the degrees of freedom of the environment that we would like to treat by classical trajectories. And this procedure gives us classical trajectories for the degrees of freedom we designate as environment or classical, but we retain the full path integral description for the system. And the reduced density matrix looks like this. It is now a phase-space integral over coordinates Q0, P0 of the degrees of freedom we designate as environment. There is a function, a phase-space density here that we sample trajectories from. Trajectories are propagated to the time qt pt to time t, and they are all the dynamics is in this function here q, which we called the quantum influence function in analogy with the influence functional. And this function q contains the effects of the system now on the environment. It's given by a full path sum of initial conditions times phases. The phases are the phases for the system, and phases arise from the interaction of the system with the environment. These are given in terms of a time integral of a function here, delta v, the potential function, and everything here is contained in this interaction. So if you look at this expression, it looks like a disaster actually, because everything here is a phase. We have to do this multidimensional integral here for the solvent, and everything other than initial conditions is contained as a phase. So it looks like we're going to have a massive sign problem. However, we don't. The way we evaluate this, we're able to evaluate this fully and converge without making any additional assumptions other than the stationary phase treatment of the environment, which again is a rigorous semi-classical treatment of the environment. So all the decoherence, everything arises from destructive or constructive phase interference here. And we have an interesting structure actually. So what we have here is the following. Each classical trajectory that we have in these that gives rise contributes to these phases supplies a phase that contributes to the expression, supplies a phase that modifies the quantum mechanical amplitude of the system, here this, because through its interaction with the environment. And we call this, for reasons I don't have time to go into, we call this the classical contribution to decoherence. Now, interestingly, each path of the system gives rise to a sequence of states as a function of time that specify a unique trajectory of the environment. And so a trajectory of the solvent coming from a Q0, P0 depends on the sequence of forces from the system. It's like, or I would say that the sequence of states that the system jumps between according to a particular path, which means that from each initial Q0, P0, I have not just one trajectory, but the full number of paths and to the number of propagation steps, trajectories of the environment. So this is the quantum mechanics, the quantum classical manifestation of non-locality, and this contributes an additional phase, which I call the quantum decoherence. And so, all right, I discussed this already, right? So, and also another nice feature of the expression is that it reverts to the full quantum mechanical result for harmonic bath, because the only approximation I've made, stationary phase, is exact for harmonic baths. And if you do a simulation, this is an electron transfer pair in solution with 1300 atoms. This converges very nicely. And what you see here is a superposition of three classical trajectories of the solvent that started at the same initial Q0, P0. And we're taking a superposition to show that the atoms have evolved to a different position along each trajectory, following a different path of the system. So you see that this leads to a form of quantum delocalization here in a solvent that is treated by classical trajectories. And again, that's a manifestation of non-locality that spills over from a quantum system to the classical solvent. And it is the effect is maximized near the electron transfer pair, the quantum system, in the vicinity of the quantum system. All right, that's QCPI. So also we very recently, in response to demand from a number of colleagues, we published our code, and there's a paper describing the code. We have a suite, we call it PASSAM. It's a suite of code that implements these methods and it's implemented in C++ as well as Fortran, and it uses various different inputs for the central module is SmartPy, because that's the most practical way for system bath decomposition, but you also have MPI and QCPI in it for harmonic baths in this code, and you can do calculations that correspond to non-adiabatic dynamics, charge transfer, extant transfer, and so on, and coupled field dynamics in this code. All right, now, how much time do I have?
About another, let's say 10 minutes, including questions and everything.
Okay, so should I go another 5 minutes maybe? Okay.
Give another 5 minutes.
So now I'm going to stop talking about methods here and talk about something related to this that I think is actually kind of nice. And let's look at the reduced density matrix that we have calculated using these methods or other methods, any method. So we can, I'm going to use this cartoon example here, say a tenside system could be a tight binding Hamiltonian or a molecular aggregate with excited states and so on. And if we take the diagonal elements of a reduced density matrix, there are state populations, we all know that, and we can plot them and see how, say, the energy starts here and how it moves around the other units in the system. That's kind of the simplest thing you can do. But the reduced density matrix contains a lot of off-diagonal elements, and these are known as coherencies. And these are quantum superpositions, really, that are kind of quenched by the bath. And they have they're complex numbers. They have real parts and imaginary parts, and you plot them like this as lines, and you get all these lines. And if you look at these for complex systems of multiple states, you really don't know what to say. So this is actually exactly what happened to us when we're analyzing the light harvesting complex. We got a lot of these, and what can we say? We can say roughly they last over, so many picoseconds, femtoseconds, picoseconds, whatever. But what else can you say about this? If it turns out that you can argue, you can say that the real parts of the, well, you can also use the information, of course, in the reduced density matrix to compute other things, such as the look at the decoherence properties or the purity of the system or the von Neumann entropy. And there's a lot of interesting physics in these quantities. So it turns out, for instance, that the purity of a system will start to decay reversibly. And if you look at it at short times, you get a sense of the how long the decoherence how long coherence lasts, but it turns out that this can actually go back up, doesn't keep decaying, and it can recover and go back to pretty high purity and all kinds of other interesting stuff here. But going back to the RDM, so you have those pictures, and what you see here is that if you look at the real part of the coherences, it does not go to zero at long times, and that's okay. That's because it corresponds to quantum superpositions that can persist all the way to equilibrium, and that's how it should be. But the imaginary components always go to zero at long times, and there's a reason for that. First of all, the obvious reason is they have to go to zero because the RDM becomes real valued when you reach equilibrium, right? But there's another reason for this, and this is because these are related to rates, to instantaneous rates. So you can show rigorously that if you are in a representation where the system backcoupling is local in the basis, in the system basis, then the time derivative of the population of state K is given by a linear combination of imaginary components of a reduced density matrix between the state K and all the other states, weighted by matrix elements of the Hamiltonian of the system alone. It's a very simple expression. So what you see here is that state population changes require coherences. Even if you are in a regime that you call incoherent, and it's like the transfer, like hopping like, you still have coherences. Without coherences, you don't get any transfer. And the other thing that this says is that you can analyze contributions to the instantaneous rate of a state. So if you see a state population is growing or is decaying, why is it decaying? Where is it coming from? What states are responsible for this? So you can extract pathways from this. So what can we do to capture all this? So instead of looking at all those lines, and again, they look very kind of random-like, and you can see very much. If you plot them in a different way, if you plot them as a square matrix, that's what the RDM is, on the grid of the states, a two-dimensional grid of the states, then you get these kinds of pictures. So here I'm numbering the axes are states 1, 2, 3, and so on, 1, 2, 3, and so on, like this. You get these pictures. And we know that diagonal elements are populations. So you look a lot on diagonal here, you can see the state populations. And away from the diagonal, you see coherences. That can be elements that are positive or negative. So blue for positive, red for negative, that's the real part. There's the imaginary part separately, green and magenta. And so you get these kinds of structures. And now if you look, there are a number of properties of the reduced density matrix and the visualizations that we call coherence maps. And these properties have to do with what you can prove rigorously for the reduced density matrix. So for instance, the delocalization, the spread of the coherence map in the direction perpendicular to the main diagonal is a characteristic, gives us a sense of the quantum delocalization, the system. And what else? If you look at the imaginary part, if you look at a column or a row equivalently of the imaginary part of the reduced density matrix, then these are the elements that contribute to the time derivative of population of the state that crosses this column with a diagonal. So if I look at, say, a second column here, this gives me information about which states contribute to the population of this state. State number 2 here, and you can see there's a positive contribution and a negative contribution, and you can see which one is bigger, and you can see that if positive is bigger than negative, then, or the other way around here, I guess, then the population of this state is actually decreasing with time, and you can look at the next time step, indeed it's smaller, and you can see the next one here is increasing because the contribution is mainly positive. So you can do these kinds of things and see where things are coming from. So this is a coherence map, but again, remember the instantaneous rates are controlled not only by the RDM, but also the matrix elements of Hamiltonian. So if you take this and multiply, just superimpose the Hamiltonian matrix, then you see that many of these non-zero coherence elements are not going to be contributing, and then you get a what we call an SSR map, instantaneous state-to-state rate map, and these are very useful for understanding pathways. All right, and here's what it looks like in a real system. Again, here's my toy example here, 10-side system like this, and I'm starting on the left edge, And this is the isolated, this is a sequence of coherence maps for the isolated system. Time zero, time increases like this in this direction, real and imaginary parts, and then time continues to increase, real and imaginary parts. And of course, for an isolated system, this will never equilibrate. So these keep slashing back and forth and giving rise to interesting, to beautiful structures that you can, again, understand at a glance. But if you couple this to a harmonic graph, it simplifies like this. So now you see that you're building populations along the chain on the diagonal. You also form coherences. The real part eventually settles into this band that is the reduced density matrix, the delocalization of a quantum system at equilibrium. When a system has reached equilibrium, the imaginary part, again, you get all these elements that have to do with which the populations of which states are changing, and eventually it dies out because you reach equilibrium and there are no population changes anymore. All right, so this is actually, I can stop here. There are some examples of this, but I think I will stop here. Yeah. Yeah.
Are the reduced density matrices evaluated in the eigenbasis of the subsystem?
Here you can do that if you want, but they're evaluated in the site basis.
Site basis.
Yeah.
Okay.
You can transform.
The reason I'm asking is because I thought the off-diagonal matrix elements are not gauging. There's a gauge choice somewhere. But when you say that they're imaginary, that means that those states have there's certain phases for the basis states that you can choose. Is that not true?
Can choose, and they come out of the expressions.
Okay.
Yeah.
The energy scales of the problem. What's the interaction Hamiltonian compared to the rest of the energies of the?
It depends on the system. So lots of examples here that I'm going to skip entirely, and maybe to answer the question, I would go to this here, the light harvesting complex, which is something that has one of the most challenging systems because all the energy scales and the temperature and everything are all on the same scale. They don't differ very much, and also has 24 states. I think I should stop here, right? I'll just skip everything here. Maybe I'll show the coherence maps for this system here. They look like this. They look very, very pretty, actually. And a lot of information. You can analyze this. Once you learn how to read this, you can analyze this and get an awful lot of information by looking at the rows and columns and these things. And so I'll just go to my conclusions here. And just wanted to mention that most of the work, actually most of the applications I did not mention here at all, were done by this fantastic student who just graduated, Shohan Kundu. His name was on the application slides quite a lot, but since I didn't go over them, here's Shohan. And so, okay, so that's it. So thank you very much. I'm happy to answer questions.
One or two more questions. I've already had a few.
Can you comment on how this classical path integral formulation is related to things like surface hopping, and in particular, I don't know if you're familiar with some of the more recent deterministic surface hopping methods that come out of Jeremy Richardson's group. Are they related in any way? Are those an approximation to this classical path integral?
So QCPI is a rigorous path integral expression, fully derived. There is nothing but stationary phase with respect to the environment. Surface hopping is not, it's ad hoc. Now, if I have a two-state system or a discrete system, then the quantum paths jump between the states. Path can be left or right, left, right, like that, right? So you can, now the corresponding classical trajectory jumps between the electronic states, right? Any path integral will do this. So you can now start making connections this way with, say, surface hopping. The trajectories hop between surfaces, but they don't follow prescriptions. They hop in all possible ways, according to all possible paths. In addition, there is no scaling, no rescaling of velocities or energies or anything like that, or with velocities or energies that comes with the path integral. You don't do that because that's what the expressions say. When I said this a few years ago, the first time at the conference, There were a lot of people saying, that doesn't make sense, that can't be physical. But now I think what I hear is that's what they say is they should remove this from surface hopping as well. So I don't know, surface hopping is not my expertise, but so there's similarities, but they're important differences.
Okay, great. Any more, any pressing question? Otherwise, we should go on.
For this small matrix formulation, when you use, say, tempo as a backend, do you construct a full exponential sum in R explicitly, or is there also some decomposition going on for that?
Exponential sum, which exponential sum?
So, as far as I understand, the small matrix formulation is exponential in R, right?
Oh, the entanglement length.
Yeah.
Yes, yes.
So do you say you use tempo as
Yes.
a backend for
Yes.
that? Do you just query all the exponentially many NR entries to construct the small matrices, or is there some other-
No, that's the whole idea, right? So if I were to use tempo, I just calculate the RDM basically at the memory length, over the memory length, over the entanglement length.
Mhm.
That's all I do. So it's not exponential, right? So it's what it is. So but depending on which regime you're in, there's a method that is actually most profitable. Like we have in the code, in the way we're thinking about this. Well, where is it back? Here it is. We have 4 different methods, maybe there are more, for calculating those matrices. Full quapi is one, it's an exponential number of paths. Glib sum is another one that I mentioned, so you can get a small subset of the number of terms. In the incoherent regime, you get away with very cheap calculation compared to total. Tempo is another way, so you don't get the full exponential scaling, and I think that's most useful for most advantageous when you have weak coupling and small systems. QCPI is another way to do it. QCPI is exact harmonic bus. It gives another algorithm, and that's advantageous when you have extremely long memory, actually. That is classical memory. So QCPI is very efficient for that. And we have a small matrix decomposition of QCPI as well.
Great, let's thank you again, and we'll go to the next question.